Okay, Ji, let's formally start our lecture for today. Today we'll be talking about word embeddings. I think I had given you some basic introduction to what it is, right? I'll just recall it. That basically, so far, when we were studying convolutional neural networks, most of the time we were dealing with image data, right? We were doing convolution on images. So we did not do any examples which were involving textual data, right? So now we are into the second half of our semester. It's week number 9. So now onwards for the next 3 to 4 weeks, we'll be looking at recurrent neural networks, right? And most of the examples that we'll see in the context of recurrent neural networks will be dealing with textual data, right? So our input would be text, and we will be trying to solve some problem which is more related to NLP rather than computer vision. So before we can do that, we need to see how we can effectively represent our textual data before we can feed it to a learning algorithm, right? So word embedding is basically the way you represent your textual data before you can solve any problem that is involving textual data, right? So I told you last time that the whole summary of this complete lecture is that word embedding is basically a process that allows you to convert text into numbers, right? And why we need that? Because our model, our network, it will need numbers as an input, right? It cannot directly work on textual data. So this is the motivation, right? And you can say from a technical perspective, the key theme of word embedding is that the meaning of a word can be inferred by the company it keeps, right? By the company we means the neighboring words, right? If you are given with a word, you can actually guess what could possibly be the neighboring words of this particular given word, right? So this is the whole idea around which word embedding revolves, right? Okay, so this I think I had discussed, so I'll just quickly revisit it that since the learning algorithm cannot directly take text as an input, so we need a mechanism which can allow us to convert textual data into numbers, right? So from if you go to classical NLP based methods, so there are different ways in which you can convert text into numbers, right? The simplest is the count vector, that you have a vocabulary of all the words, right? And you make a histogram that, okay, this particular word 1 is appearing 2 times, word 2 is not appearing. Similarly, word K is appearing 50 times. So you have something like this, that how many times a word is appearing in this document, right? So which can actually be a descriptor for that particular article or text, whatever the data is, right? Then we have term frequency, inverse document frequency, again from NLP, and it is also used in IRT based systems. And then another method is co-occurrence matrices, where you count how many times a word appears with another word, right? When you say co-occur means to occur together, right? So you count that, okay, whenever I see this word, I also see this word. So you can actually make a complete matrix in which you count how many times words are occurring together, right? But what we are looking at, word embedding, it is basically a prediction based embedding. It means rather than these rules or these frequency based embedding, we actually learn how to convert, you can say, textual data into numbers or into vectors, right? So within that, we have two commonly employed methods. One is the GLOVE, which is by Stanford, and the second one is word to vector by Google. So most of our discussion will be based on word to vector by Google, right? So previously, we have been representing our data using one-hot vectors, right? For example, when we are solving classification tasks, where the number of classes is not, you can say, a very huge number. Maybe even in ImageNet it is 1,000, right? But once you are dealing with textual data, you have a vocabulary of words, right? And the size of vocabulary easily could be maybe 10,000 or even 100,000 or even more than that, right? So if we represent data or we represent words using one-hot vectors, so of course one obvious disadvantage is that you will have a vector, right, which is taking a lot of memory because there are 10,000 values. So it is very sparse, right? Everything is zero. There's only a single one, maybe at one single position, right? So this 5391 is just a random number which is telling you that we are representing this word man by a vector in which everything is zero except for this position which we have picked 5391. Okay, this is just for discussion purposes. So you see, this is basically one disadvantage. But another disadvantage which we discussed towards the end of the last lecture is that when you are representing your words using one hot vectors, uh, there is no relationship between two different words, right? So I had given you this example that if we have two sentences, have a good day and have a great day, so both of them are actually trying to convey the same meaning, right? In the vocabulary, we have 5 words. We can represent every word maybe by a vector like this, right? So the problem is that if you see what is the relation between good and great, okay, so if you take their dot product, it will be 0, right? Or even, or maybe if you take their Euclidean distance, right, it would be like maybe 1 plus 0 plus 0 square under root, and then you add. So basically, the Euclidean distance or the dot product of these two is same as if you compare maybe good with some other word like article a or day or have, right? So in other words, there is no relationship between two words. Good and great have same relation as day and have, or good or chair or apple, right? Another example illustrating or elaborating the same idea that normally with recurrent neural networks will be trying to make a language model, right? That we have a lot of text and we'll train a model and we'll say, okay, we give it a sequence of words and it has to predict the next word, right? So for example, if the model is already trained, maybe we give it a sequence of words, I want a glass of orange, and model is able to predict that the most likely word which should come here should be a juice, right? Now suppose this problem is solved by the model, right? But suppose now we have a situation where we ask the model, okay, I want a glass of apple and what should come here? So if you see, ideally, if your model knows that orange juice is something popular in summer, then this should be a trivial problem because apple juice should also be something popular. But the problem with one hot representation is that the model has no way of actually judging that orange and apple are actually similar things. They are both fruit, right? In one hot representation, the relation between these two is same as orange and chair, or apple and man, or orange woman, anything, right? So you see, there's no actually similarity between you can say these different words, right? So you can, as I told you, that if you take the inner product or the dot product between any two words, it will always be 0, right? Or you can also find the Euclidean distance between any of these two vectors. So whatever you compute between these two vectors, you will get the same value if you compute its distance with any of the vectors, right? Because you just have a single one and rest everything is 0. So in order to address all of these challenges, rather than using one hot representation, we'll be using a learned representation, which we will be calling word embeddings, right? So in order to intuitively understand what are word embeddings, first we see a hypothetical example, again, a very famous example from it's available in different books and tutorial as well. So I have just taken it from there. So you see, these are our words, okay? And this 539198853, these are the positions that you have a 1 if you represent it using one hot representation, right? So instead of that, we just take a hypothetical example that, okay, for each word we identify certain features, okay? For example, the gender of the word, of course in some cases it would be meaningless, right? Maybe for a fruit there is no gender, for a king and queen there is gender. Then the degree of being royal, the age related with that word, whether that particular word is referring to something we eat or not, right? And we say that, okay, every word can have a value in the range -1 to +1. Okay. So for example, we say that for a man, we have say gender is -1, for a woman, the gender is +1, right? Similarly, for a king, the gender is a male, so it is a value close to -1. Queen is a female, so the value is close to +1, right? And for these two words, which are fruit, there is no gender associated with it, with these words, apple and orange. So the value of gender is close to 0, right? Similarly, you can say, okay, man and women, they are common people, they are not royal. On the other hand, king and queen are royal, so they have a value which is close to +1, right? Because they are royal. And similarly, for orange and apple, nothing like that is associated, right? Similarly, maybe if we consider food, so since these first 4 words, these are not the things we eat, so we have a value close to 0. On the other hand, these two are actually fruit, so we have a value which is close to, you can say 1. Now, if you see and compare these vectors, so now you see if I compare the vectors of man and woman, they are very much similar. The only difference is gender, and that's the way it is, right? Similarly, if you consider the last two columns, okay, apple and orange, so you see um, their vectors are very similar. Of course, for this example, we have taken only 4 features. Maybe we'll have more features, so there will be some differences between the two. For example, the color or the weight, right? But still, many of the values would be common, right? So this is the whole idea of word embedding, that the words which are similar, they should appear together in the feature space, right? So this is basically, you can say, an illustration that the words which are similar, when I represent them by vectors, their vectors should also be similar, okay? So actually, when we'll be solving it, the dimension of the vector would be like a big number. Normally in word to vector, the standard dimension is 300, right? But since we cannot visualize in a 300 dimensional space, so for visualization, normally we apply PCA and we bring our data back to 2 or 3 dimensions, right? So this is just a visual illustration that you see the similar words, they are appearing together. Maybe these are all animal, these are all fruit, these are digits, right? So they are actually, their vectors would be, if I have origin somewhere here, so the vectors of these words would be very, very close to one another because they are representing the simple concepts. Now, what would be the advantage of this representation over one hot representation? We try to convince ourselves with this example that suppose we come back to this problem of named entity recognition, where we feed a sentence to our model, and for each word, the model has to tell whether it is name of a person or not, right? It's a very common problem when you are dealing with textual data, that you have to identify names of persons, names of places, names of companies, right? So that you can automatically process the data. So, for example, if we feed it with this example, say Sally Johnson is an orange farmer. So all the words which are names of a person, we expect a 1 as an output. And all the other words which are not names of the person, we expect 0 as an output, right? So for this first statement, we get this as an output. Now you see, if we are representing our data using word embeddings, then the model can generalize very well. Suppose next we feed it with this sentence, Robert Lane is an apple farmer, and the model has to predict for this particular sentence that where are the names of people, right? So now, since orange and apple, their vectors would be similar, both are fruit, right? So your model will learn implicitly that if orange farmer is a person, then apple farmer should also be a person. So you see, now your model will generalize that since both of these things are similar, so if orange farmer, which was this guy, it was name of a person, it is highly likely that apple farmer is also a person. So your model will say, okay, names of people are coming here. So you see, this is actually allowing you to generalize the findings. Another application of word embeddings is reasoning, right? Maybe you have attempted some competitive exam where there's an analytical or reasoning section, right, where you see questions like this. Okay, man is to woman, asking is to, and you can easily guess that the answer is queen, right? There are many questions in different competitive exams like this, so you can actually solve them. If they are based on textual data, not numeric data, you can solve them using word embedding, right? How can you do that? That you see, if you see the vectors corresponding to man and woman, all of these values are almost same. The only difference is gender. Similarly, if you compare king and queen, again, most these values have similar values for king and queen. The only difference is gender. So you see, the difference between man and woman is that of a gender. Similarly, the difference between king and queen is also that of a gender. So both of these actually are, you can say, pairs. So if we have a question like this, we should be able to predict that the answer to this question is queen. And how we can do it numerically, right? So you see, if you take the difference of these two vectors, so you see minus one, this would be minus 2. And since both of these values are similar, so approximately they all will be 0. Similarly, if you take the difference of these two, so everything is approximately 0, and you get a value close to minus 2 here, right? So both of these vectors are more or less similar. So how you can actually solve it, that if you have to find the queen, so you know that the difference between man and woman, their vectors, should be same as the difference between king and some vector. So you actually have to search for the right vector, which you subtract from the vector corresponding to the word king, and the answer should be close to the answer you are getting on the left hand side, right? So, or you can actually simplify it, that maybe you can take it here, or maybe the reverse, you can bring these here and you can take this e here. So actually you have this expression, okay? Vector of king minus vector of man plus vector of woman, right? And you have this vector 300 dimensions or whatever is the dimension is, and you have to find another vector w out of all the words, so that the similarity of this with this is maximum, right? It means you are searching for this vector EW because you don't know the answer, which is queen. So you have all the vectors corresponding to all the words, and maybe queen is somewhere here. This is chair, table. So you have to find that particular vector out of all of these, which is giving you, you can say, the maximum similarity with the vector which you are getting from here, right? So you can actually write a program which can solve it. And how do we compute similarity between two vectors? There are different ways, right? But a standard way is that we compute the cosine similarity. Now, why it actually gives us similarity between two vectors? Because you see, if I explain it in a two-dimensional space, I have one vector here, another vector here. Okay, so this is v1 and this is v2. Okay, so if you take their dot product, right? So dot product is something like v1 v2 is v1 magnitude into v2 magnitude into cos theta. Okay, so you can rearrange this, so you will actually come up with something like this. So now you see, you are actually computing this number, which is the dot product of two vectors divided by the magnitude of both the vectors, and this is equal to cos theta. Now if you remember trigonometry, cos of 0 is 1 and cos of 90 is 0. Okay, so if these vectors are very close to each other, right, this theta is close to 0, maybe nearly equal to 0. So this would be close to 1, right? Because the maximum value of cos is 1. Similarly, if these vectors are far apart, like at 90 degrees, then cos of 90 is 0, right? So this number would be close to 0. So if this angle is small, it means both of these vectors are close, right? Of course, we are discussing in a two-dimensional space, but maybe in a higher dimensional space, it is difficult to visualize, but the same concept applies. So cosine similarity can be used to compare two vectors, and this way you can write a simple program which can solve reasoning questions, right? So now if you have a program like this, you can easily answer questions like if Ottawa is to Canada as Nairobi and this is missing, so your model can actually predict that this should be Kenya, and similarly yen is to Japan as ruble is to, and you can predict this Russia using a model, right? So this actually tells us that word embedding is a useful representation, right? So, and this is the representation that we will be using when we are processing textual data using our neural networks. Okay. Now, okay, we are convinced it's something good, but how to actually convert your data or one hot representation into vectors, right? This is the part we have not discussed yet, right? So actually, for that, we have to learn a matrix, and that matrix is called embedding matrix, right? Now, what does it mean? That you will have your data represented as one hot vectors, right? Suppose your vocabulary is 10,000, so every vector is of size 10,000. Okay, you say, okay, I want my vector to be of length 300. So you need to learn a matrix. This is the matrix which you will learn, which we are calling embedding matrix. And the size of this matrix in this case would be 300 cross 10,000. Now you will multiply this matrix with your data, which is in this form. And for every word which is represented as a vector, you will get the corresponding vector, right? It means every word in your corpus will be represented by a vector of 300. Why 300? Because we have chosen 300 here. If you want to be 600, the size of the embedding matrix would be 600. So every vector would be 600, right? But 300 is the standard size that is chosen by many implementations, like word to vector, which we'll be looking at, right? So this basically, let's see in more detail how word to vector works and how actually it learns the embedding matrix. So as we discussed in the beginning of this lecture, that actually we exploit the idea that if we see a word right? What are the most likely words we can expect in the neighborhood, right? For example, if we see the word vehicle, then we can guess that vehicle is associated with road, engine, drive, seat, and so on, right? Similarly, if we see the word moon, then we are likely to see in the same context words like space, landing, NASA, star, rockets, right? On the other hand, maybe we are, if we are talking about moon, maybe will not be talking about Python or a projector or a chair. It is unlikely. Of course, it can be theoretically, but it is unlikely, right? Similarly, with moon, maybe we are not talking about a car or a clock, right? Something like that. So with word to vector, you see the idea is that you can actually load it in a program, right? And you can give it a word, and you can say, okay, I want all the words which are similar to this word. Okay, so just this is the actual output which I show you on the screen. That okay, word to vector is already implemented, so we can download it and we can just give it a query word, and we can say, okay, what are the most similar 5 words to this query word? Okay, for example, in my example, if I feed it with the word polite, okay, so it gives you few sorted most similar words. So the first one is courteous, and the similarity, cosine similarity is 0.9, which makes sense. Then friendly, cordial, professional, and so you see that you also have, you can say, their similarity score, and you have a list of words which are similar to this word. Okay, and this is actually learned. So you see, you can implement a model which can replace words by their synonyms, or it can work like a dictionary where you can use word to vector and find similar words. In the second example, instead of a noun, we are giving it a proper noun like a country name, France, right? So you see, again, the similarity is not very high, but still if we sort it, then you see the best match is Canada. Why Canada? Because maybe there are different regions in Canada in which you speak French, and in France also you speak French. Why Germany and Spain? Because they are neighbors. So you see, there is some reason why we are getting these, right? But of course, the first example is more intuitive, that you have a word and you have synonyms. For proper nouns, since we don't have synonyms, so still we are getting something which is quite meaningful, right? So word to vector, as we discussed earlier, it will convert every word in a vector of 300 dimension. And for visualization, if you plot those words in a 2-dimensional or a 3-dimensional space, so you see all the concepts which are related, their vectors are similar, right? Maybe these are related to kitchen, these are related to electronics, and so on, right? So it is actually to some extent generating what we expected, right? So this slide shows you a very limited vocabulary, right? Ideally, practically, you will have a vocabulary which is very huge. So practically, you will be getting something like this. Okay. So you see, you have a big corpus of 10,000 words. So maybe if you plot them in 2D or 3D, so you'll be getting something like this. Okay. Now let's see how this embedding matrix is learned, right? And we'll be talking in the context of word to vector. So in order to learn embedding matrix, we again use a neural network, but this time it is a shallow neural network, right? It is not a deep neural network. So it is typically a 2-layer neural network, right? In which we feed our corpus in a specific way, and eventually it gives us the embedding matrix, right? So this network itself is not deep, but when it converts your words into vectors, then subsequently those vectors can be fed to a deep neural network, right? But the network itself, which is learning the embeddings, it is not a deep network, right? Okay, now how do embeddings are learned? There are 2 different methods. They work more or less in a similar fashion, but the approach is different, right? The first one is continuous bag of word, right? CBOW, where what we do is that using the context, we try to predict a target word. Okay, I'll show you an illustration on the next slide, right? Let me just give you the definition of both, and then I explain with examples on the next slides. The other one is skipgram, where you are given a word, and from the word, you try to predict what could be the most likely context for this word. Okay, so both are actually the same thing. The way you approach is actually different. So in CBOW, continuous bag of word, your context is this. Okay, and from the context, you are trying to predict this word, which is jump. Now, context can be a single word. Maybe fox can be a context. Context can be 2 words, one on the left, one on the right, right? So for example, your context could be 1 word on the left, one on the right. Context can be 2 words on the left, 2 words on the right. It depends what is the length of the context you are talking about, right? Similarly, if you take the reverse case, which is skipgram, so in that you are given with this word and you are trying to predict the context. Maybe what is the most likely word on the left or the right, or two most likely words on the left or the right, or three most likely. It is something like that. Okay. So now let's do this example in detail, that how this network will be built and how would be able to learn the embedding matrix. Right. That suppose we have this, maybe have a great day. Okay, and suppose we are talking about a context of only one word. Okay, so we'll make a neural network. Okay, and suppose we are focusing on this part of the text. So we say, okay, when the context is great, okay, which is input, the output is day. Okay, so from this we are trying to predict this. Suppose you want a context of two words, one on the left, one on the right. So what will do, what would be there? You will be feeding one word, which is a on the left and day on the right, and you will be trying to predict the center word, which is great. Okay, so I'm using a context of one word on the left, one on the right. Okay, similarly you can use 2 words, 3 words, and you will do this for your complete corpus. Okay, so first let's develop the general idea using a context of one word, and then we'll extend the same idea to multiple words, right? So as I told you, it is a shallow network with only 2 layers. Now what is going on in this network? This is your input word. How is it represented? It is represented as a one hot vector. It means it is a vector of say 10,000. You are feeding a word. What are you predicting? You are again predicting a word. So this is your output again in one hot representation. Okay, and the size is same as 10k, right? Because our vocabulary size is 10,000. So the input is 10k, the output is 10k. Input is a word, output is a word. Both are one hot encoded, right? Now this is your hidden layer. In this layer, you will choose some size. For example, we say we have 300 neurons, which is a standard size you will find in most of the implementation, right? So you see now what will happen. You have a weight matrix here, and the size of the weight matrix is 300 cross 10,000. Okay, similarly, the size of this weight matrix is 10,000 cross 300. You will train this network, right, on your entire corpus, where you feed one word and you predict the next word. And once the model has trained, this is the matrix that you will extract. You will throw away this model. This is actually your embedding matrix. If you remember, we discussed in the beginning that we need a matrix of 300 cross 10,000. So this is actually that matrix which you will keep. Okay, and how it works, it will become clear in the subsequent examples, right? An important thing is that when you are making this network, so this layer has no activation function, right? We are simply taking the dot product here because we are just trying to learn this matrix. But of course, at the last layer, since we have to convert it back into one hot vector, it will have a softmax activation function as the last layer. But the hidden layer does not have any activation function because we just want to learn that matrix, nothing else. Okay. Now, if instead of a single word, we have a context of multiple words, say 2 or 3 words. So what we'll do, we'll feed all of these to this hidden layer. Okay, but this weight matrix is the same, and here you are actually taking the average of all the vectors, right? You are getting a vector from the first word, the second word, the third word. You will simply add them together. You will divide them by 3 if there are 3 words. So you are only computing average. Okay, so it's fairly simple. If you have one word, you just feed it. If you have multiple words, you just compute the average and then you feed it. Okay, now let's see a concrete example with some limited vocabulary rather than 10,000 to understand how this process works. Okay, so we have a limited vocabulary of 5 words only. Okay, so every word is represented by a vector of size 5. Okay, and we are doing this example with continuous bag of word. Okay, we are using a context of 2 words, means one word on the left, one on the right. Okay, so this is our text. Of course, you will have millions of sentences like this. So we say, okay, I want to predict can, which is my target, okay, which is represented by this vector. And my input is one word on the left, which is hope, and one word on the right, which is set. So this vector is hope, which you see on the top, 1, all 0. This vector is set, 0, 0, 1, 0, 0, okay. So we are feeding these as input to a network. In the hidden layer, let's say we only have 3 nodes. Okay, so I have 3 nodes here. Okay, and then in the output, we are predicting the word can, which is again represented by a vector of 5. So you have 5 neurons here and softmax activation function. Okay, so your this matrix is 3 cross 5. Okay, and this matrix is 5 cross 3. So initially what you will do is, and by the way, both of these matrices are actually the same. They are not different matrices, okay? They are shared. So this is the same matrix. You are simply computing the average and then you are computing the output. So you will, this is your first training example where you are feeding 2 words and you are predicting the central one. So of course, weights are initialized randomly. So initially you will get something here, which is totally garbage. You will compute the error with the actual target. You will back propagate the error and update these weights just like we do in any other neural network. Okay. Then what you do, you take the next example. Okay. So now your input is set and free, and you are trying to predict the central word, which is you. So you will keep on doing this for entire data set. And eventually, once your model is trained, you will extract this 3 cross 5 matrix from that model, right? We don't need to keep that model. You can throw it away. All you need is to keep this matrix of 3 cross 5, which is our embedding matrix. Now, if the same thing you had to do for skipgram, you just have to reverse the model that from this word can, which is now input, you will be trying to predict what is on the left, what is on the right. So this is actually your word hope, and this is your word set, and the rest of the mechanism stays exactly the same. You will be training this model and you will be extracting this embedding matrix. Okay. Now, once you have this embedding matrix, now you can convert all of your data into vectors of size 3. Why 3? Because in the hidden layer we had 3 neurons. Okay, so this is your embedding matrix and this is your complete data. Okay, suppose I want to convert this hope into a vector, not one hot vector but a vector of size 3, because I had chosen 3. All you need to do is multiply this vector by this embedding matrix. So when we multiply it, we get this. Okay, now you see there is a pattern in the multiplication. When you will multiply this matrix with this vector, what will happen? You multiply W00 with 1. These are all multiplied with 0, so they are gone. Similarly, you multiply the second row. This is multiplied with 1, and they are all multiplied with 0. This is multiplied with 1. They are all multiplied by 0. So eventually, you get back the first column of this matrix. You see? Similarly, if you want to convert the word you, okay, so you can guess it will actually be this. You will, if you multiply, you will get the fourth column of this matrix. So you see, now it is like a lookup table where you have this matrix, because every time you are converting a word, one hot represented word into a vector, you are multiplying by a vector in which everything is 0 except a single value, that is 1. So that 1 is actually picking up one of the columns of this matrix, and that vector which you have in this matrix is representing that particular word, right? So again, the same idea represented differently, right? That you have single word, we just have taken transpose here. So you are actually picking up just like a lookup table, a row or a column from this matrix, right? So the example we did, it was fairly a limited one because we needed to understand the concept, but practically, of course, you will have millions of sentences, right? And in our case, the vector size was 3, but typical size, as I told you earlier, is 300, right? As you will see in word to vector. Now, if we compare both of these representations, that is one hot representation and word embedding representation, right? So you see, one hot vectors are sparse. Sparse means everything is 0. There's a single one. On the other hand, these are dense matrices, right? You have some value at every position in the vector. One hot representation is very high dimensional, 10,000, 100,000, or even 1 million, right? On the other hand, this is low dimension. You can control what is the dimension that you want, right? Likewise, if you're talking about one hot coding, they are hard coded, right? Then nothing is learned. On the other hand, when we talk about word embeddings, they are actually learned by looking at your data, right? So everything is indicating that this representation in word embeddings seems to be much better than what you expect from one hot representation, right? And this is something which I told you earlier, but now it will make more sense, that one hot representation is like, you see, everything is on one axis, right? For example, this can be 100, because we are in 3 dimension. This could be 0 1 0, and this could be like 0 0 1. Okay, so that all of these are at 90 degrees. So if you take the dot product of any two vectors, you get a 0. Means there is no relationship between these vectors. On the other hand, once you represent them with word embedding, so you see normally if it's a stuffed toy, it is likely to be soft. So these two words are likely to be somehow related, maybe not that closely, but still they are more related to each other as compared to book. Okay, so that's why now their vectors are relatively close. They have some sort of similarity, and book is somewhere else, right? So similarly, you will have many vectors, and all the words which are similar, you expect them to group together, right? So if you want to do some natural language processing, there are different libraries available, right? For example, this is one of the famous libraries which also provides the word to vector class. Okay, so I will not be doing this, no assignment on this. I'm just showing you this code only. If anyone is working in NLP and they want to reproduce something, it's only for that purpose. Otherwise, we will not be doing that in much detail, right? So basically, you see, I created a small corpus with some sentences. First sentence, second sentence. Of course, this is a very small corpus. Actually, your data would be coming from maybe a complete novel, the complete literature which is available online, right? So I'm just telling you that you can use word to vector to actually convert words into vectors. This is already learned, and then you can visualize them by applying PCA. Okay, you apply PCA, you convert every vector into you can say 2 dimension, and then you can plot. Okay, so you see our data was you can say very few sentences. That's why it may not be very meaningful, right? But still, you can find some clusters, though they are not very meaningful. But if you train the same thing rather than on these 5 or 6 sentences on a larger corpus, so you expect that you will get something that is meaningful, right? Similarly, there are some good online demos which are available, right? So maybe I can show you one of those if there's something, right? So now you see it is basically, I hope you can see this rotating sort of blob or whatever you want to call it, right? So this is actually word to vector of 10,000 words, right? So you see, if I take my cursor, it is telling you the word. Okay, so you can actually see it, you can zoom it. Okay, so you see, so these are different words on which PCA is applied. You can see on the left side, and these are 10,000 words. They have been reduced to 3 dimension, so you can actually compare that. Okay, which are the words which are close to you can say one another. Okay, there of course there is much more in this demo. You can choose the dimensionality reduction method. You can also change this word to vector, and you can maybe map it to 2 dimensions rather than 3 dimensions, right? So if you're working in NLP, this could be a good demo that will help you understand many concepts, right? Okay, so maybe we can take a short pause here so that if you have anything to ask, we can spare some time for that. Okay, so next what we'll see is related to this, right? But it will be more applied in the next topic. So I'm just introducing you to this, which is convolutions in text, right? And more specifically, we are talking about 1D convolution. So you see, previously we have been applying convolutions to image data, right? And almost more than 90% of the literature that you will see, people will be using convolution on images, right? But there are possibilities in which you can apply convolution on textual data as well, right? So this is actually a very famous paper that exploited this idea, that convolutional neural networks for sentence classification. Now, if you look at the title, it looks a bit strange, right? Because we know that convolutional neural networks are typically used for image data, right? Because you have an image, you apply convolution, you learn feature. So this is an application of CNN on textual data. Means you are applying CNN on NLP, which seems a bit strange, right? But one important thing here is that when we are talking about convolution here, this is actually not a 2 dimensional convolution, but a 1 dimensional convolution, right? So if you see on the right side, these are snaps from the reference which you see at the bottom of the slide. So in an image, this is our filter. Okay, you move the filter in towards right, and when you reach the end of the image, you go back to the next row. Okay, so you see now your filter is moving in 2 dimensions, in the horizontal dimension as well as the vertical dimension, right? So your filter is moving horizontally. When it reaches the end of the image, it goes back to the next row. Similarly, the same process is repeated until the convolution is applied on the complete image. So here, image was 2D, that's why convolution is performed in 2 dimension. Now, if I have a text, so text is, you see, just a sequence of words which is 1 dimensional. Okay, of course, when you are writing text in a word processor or a book, you see it as 2D, but in memory it will be 1D, right? You have a sequence of words. Since you have a limited length of page, so you go to the next line when you are writing in a word processor or you are printing a book, but actually it is a 1 dimensional data. You can just keep on reading text, right? So there's no second dimension, there's only 1 dimension. You can just put it as a sequence of words, right? So if this is my text and this is my filter, so you see, I have a sequence of words and I will keep on moving my filter. So my filter is moving only in the one direction. Okay, even if you take this example where I write words horizontally, so my filter is moving only in this direction. Okay, so that's why when we are doing convolution on the text, we talk about 1 dimensional convolution, that is not 2 dimensional convolution. Okay. To further explain this idea, let's see an example that we have few words. Okay, so these are the words which you see in green here. Okay, maybe this is go, come, anything. Okay, and every word is represented by a vector. What is the size of the vector? 1, 2, 3, 4, 5, 6, 7. Okay, so this one word is represented by a vector of size 7. Similarly, the second word, and so on. Okay, now when we will design the filter, since the dimension of vector is 7, so it is understood that filter will have 7 values. When we say length of the filter, we are talking about how many rows it will have, right? Because the number of columns is fixed. Just like if you remember when we were doing convolution on images, we say that the depth is fixed. Okay, you can talk about how many rows and columns. Depth is always equal to depth of input. It is a similar concept here, that the number of columns here is fixed because the input vectors are of size 7. So your filter has 7 columns. When we say length, we are talking about rows. Okay, so the length of 2 means 2 rows. Length of 4, it means 4 rows. And your filter will be moving in this direction and producing the output. Right. So now this is the same, you can say, concept, but illustrated with numbers. You have a vector for every word. Size of the filter is 2. So I superimpose my filter on this part. I perform convolution, I get a number which I write here. I move my filter 1 position down. You see, I do convolution, I get this. So I will keep on moving my filter. When I reach the end of the text, I stop. So you see, I am only moving my filter in a single direction. Again, the same concept illustrated visually, right? We have placed the filter, the size of the filter is 2. We place here, we get 1 output. We move the filter 1 position down, we get the second output, and the last convolution actually gives us this output. So actually we get these 4 values as the output of this convolution. Now you see, this was one single filter. I can have another filter like this. Okay, so you have one filter which is giving you these 4 outputs. You have, this was first filter, this was second filter, which is giving you this. And of course you can have multiple filter. And what you can do, that for this filter you can say, okay, I will only keep the maximum value. For this filter output, I will only keep the maximum value. So you keep maximum from the output of first filter, maximum from the output of second filter. You get these two, you can concatenate them, and then again you can apply maybe another convolution or feed these to fully connected layer to do some sort of classification, right? So again, just to illustrate you the application, this is an illustration from a paper where they are showing that they have textual data and they have multiple filters of different sizes. You see, these are the 2 filters of size 2 because they have 2 rows. Then these are filters of size 3, the green ones, and then you have filters of size 4. Okay, so you apply convolution with each of these filters. Maybe this is giving you this, this is giving you this. You apply max pooling and you concatenate the two. Similarly, you do the same thing for the green filter. You apply max pooling, you get this. You do the same thing for filter of size 2. You have 2 feature maps, you apply max pooling, you get this, and then they say, okay, concatenate this. So you can say a very rich feature vector with multiple sized filters applied to the textual data, and eventually you can apply a fully connected layer with sigmoid or softmax to actually solve some sort of classification problem, right? So this was, you can say, 1D convolution on textual data, right? Which we'll be actually using in the subsequent lecture, right? So both of the topics that we have seen in this particular discussion, the first one was word embedding and the second one was 1D convolution. This is actually, you can say, building up for our next topic, which is recurrent neural network, right? So before moving to that, if you have some questions from this particular topic, we can discuss those. Thank you.